Yes, yes.
Can you see my screen now?
Yes, 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 we can see.
All right, then I will do it without
Yes.
stop. All right?
Yes, yes, yes.
Okay. In case something wrong, please call me.
Yeah, yeah, sure, sure.
Okay, thanks.
Okay, thank you.
Okay, good morning. My name is Leehter Yao from National Taipei University of Technology. I would like to share with you some of my experience with some of my experience of integration AI with machines. And with this topic, I'm going to share with you some of my experience building autonomous mobile robots and robot fish. Sorry. Okay, this is my outline. So if we are going to integrate AI with machine, there are several things we need to be careful. One thing is that we have to design our AI with real-time functionality, because if we are going to integrate AI with machine, usually we have to make AI functions very fast. Okay, in other words, we have to make AI has the real-time functionality. And the second thing we have to worry about is the real-time sensing, communication, and actuating, because usually we also have to design the entire system to fuse all the sensor information and through some communication schemes. And based on the sensing information, we have to control our AI to actuate some actuators, for example, motors or something like that. And of course, because we cannot put the complete computer system into machine. So usually we will have to have embedded system. In other words, we have to have a simple version of the computer. And when we design the AI algorithm, of course we want it to be efficient and fast. But at some stage, we also need to worry about energy, because the battery we carry with the machine is very limited. So on one hand, we want to design fast, efficient AI algorithm. On the other hand, we want this AI algorithm to be energy efficient also. So and we also need to have a efficient operation system. Usually we will use ROS, because ROS will in this environment, in this operating system, it will be more convenient for us to integrate all sensors, different kind of communication schemes, actuators, and also computational algorithms. And finally, if it is necessary, we have to update our system from time to time. Just like when we see, for example, the iPhone will have to update our system from time to time through Wi-Fi or through mobile communication network. So that is called OTA, that is over the air. Okay, so this is another issue we have to worry about. So the first thing I'm going to share with you is a typical example of integration of AI with machine. That is, I call it hospital rover. So my hospital rover is motivated from the idea that, well, we usually take public transportation or we drive car from one place to your destination, but is it possible we could we don't have to drive ourselves in order to carry some objects? So we are going to design an autonomous robot so that this robot can carry objects for us. So the hospital rover comes from my campus rover. This is my first generation. I'm sorry. this is my first generation and second generation. And some professor in our industrial design department designed the outlook for me, so it looked more beautiful. So in this campus rover, we have LiDAR. We have 3D LiDAR on the top. We also have 2D LiDAR at the bottom. And we have some robot arm to operate the elevator. And we also have the depth camera to not only to sense the images, this camera can also measure the distance. And of course, we have some actuator. There are 2 motors to drive this vehicle. And underneath the LiDAR, we also have another camera here. So this camera is to measure the distance, and this camera is to do object recognition. Okay, so if we see my goal is to design an autonomous vehicle or mobile robot for indoor use. Okay, I'm not going to compete with Tesla or Benz or BMW. They have thousands and thousands of brilliant engineers to design autonomous cars running on the road. Okay, and so there is a space for us to design the so-called indoor autonomous vehicle. So that's why I was motivated. So I want to design my indoor use autonomous vehicle. So, and of course, some of the functions I have to be before my design. I have to make sure that my indoor autonomous vehicle has also a limited function of outdoor self-driving capability. Okay, and of course we have to emphasize the self-driving in the indoors in the indoor space. Okay, and of course the indoor environment is much more complicated than outdoor environment. So we also have to have the capability to do environment recognition, and most of the time the building is full of people and stationary obstacles. So obstacle avoidance technology is also very important for the indoor autonomous vehicle. And since the mobile robot is operating inside the building, so if we want to go from this floor to the other floor, we need to have we want to design this robot to be capable of operating the elevator. So that's why we have to design this robot arm to press the bottom of the elevator. And because this robot is running inside the building, so we also have to be careful about the safety. And finally, we also have to have good human interaction interface so that it will be friendly to the users. And because we want to design the robot to deliver objects from one place to the other place, so we don't want this. See, for example, we have the drawer here. And we put the object we want to deliver inside this drawer. So during the traveling, we don't want any other people who is not the one to be sent to open the drawer easily, so that the object can be taken by people who are not the target personnel to receive these objects. Okay, so we have to have a good authentication authentication technology to make sure that the one who opened the door is the one we want to send the object to. Otherwise, anyone else cannot open the drawer to take away the objects. And during the traveling, we also have to have some lighting and audio signaling technology to remind pedestrians that this robot is coming. Okay, so that the pedestrians will be more careful about this mobile robot. So the robot was designed entirely by ourselves, by our students in our lab. So we first have to design the motion control, and we find the most appropriate motors and gears to install this robot. So we also have to worry about the odometry of the robot, so that we know where this robot run, and we can calculate the path of this robots. And then we also have to have a capability to design the traveling route or the traveling path. Okay, before doing that, we have to use the so-called SLAM, simultaneous localization and mapping technology, to be so that this robot is able to correct the map inside the building. Okay, this is the, for example, this is, see, we before designing the path, we control the robot to go several times of the environment. So this mobile robot is going to travel, and so that during the traveling, we could collect the map information, and then we collect this map information. Then based on this map information, we will be able to design our SLAM. And then we design based on the map this mobile robot collects. We then design we have to design the route, and we put several decision points here, so that wherever this robot is called to go, this robot is able to automatically calculate the route, the best route. Okay, so in this mobile robot, we use so-called Dijkstra routing algorithm to automatically calculate the route. And then during the traveling, we also have to design a CNN to recognize the objects this mobile robot might encounter, because especially this robot is going to be used in the hospital. So we have to recognize pedestrian, we have to recognize wheelchair, the bed, or kind of vehicles used in the hospital. And of course, at the same time, we also have to recognize the stationary obstacles, and of course the elevator also. So we will not only use the LiDAR to recognize the obstacles, we also have to recognize what this obstacle is, whether it is a moving obstacle or stationary obstacle. And based on different object we can recognize, this robot has to have different reactions. So in order to do that, we first use our LiDAR this is the point cloud collected by the LiDAR. So this is the point cloud. But as you can see, this we can see the pedestrian, and we can also see the walls, which are the stationary obstacles. So in order to design our obstacle avoidance algorithm, we then take away the stationary environment, and then this picture are the images, are the point clouds for only the moving obstacles. Okay, and then we design the algorithm to track those moving obstacles, which are pedestrians mostly, so that we could estimate the direction and the velocity of those pedestrians, so that we could design our obstacle avoidance algorithm based on the velocity and of course the velocity include the condition and the speed of those moving obstacles. And so and then of course not only using the 3D LiDAR to detect those moving obstacles, we also have to figure out what those moving obstacle is. For example, if it is a wheelchair, or if it is a bed moving in the corridor, so the mobile robot will have different reactions. For example, if it is a pedestrian only, then the area of this pedestrian occupied is not that much. But if it is a wheelchair, the area occupied by this obstacle is a little bit bigger. And if it is a bed, okay, bed moving, usually the nurse will move the bed from one place from one room to the other room. Then the bed will occupy much more space in the environments. So and usually the bed move a little bit slower. So with different kind of moving obstacle, first detected by the 3D LiDAR, then we use sensor fusion technology to make sure that what this object is. Then we design different obstacle avoidance approach for different obstacles. Okay, so and of course, in order to better estimate the velocity of the moving obstacles, we have to design Kalman filter so that it will the velocity can be estimated more accurately. And this is a environment in the hospital. Okay, so we have to use CNN to we train different objects, many different objects, and that would this mobile robot might encounter in the hospital, so that we could recognize. I hope that 90% of the objects in this robot might encounter in the hospital. All right, so and then based on the obstacles, based on the sensor fusion of the 3D LiDAR and the camera, now we are able to know the objects. Then we design the reinforcement learning to do obstacle avoidance. The reason we use real reinforcement learning algorithm is because the indoor environment is much more complicated than the outdoor environment, and the space we could avoid the obstacles is very limited, and it's also, of course, it is also very complicated. So we would like to use reinforcement learning algorithm. Unfortunately, so far application of reinforcement learning to the indoor robots, it is still a very tough topic. Okay, people in this area are still working hard to do this because the indoor environment is really complicated, and of course reinforcement learning is very hard to design and to train. Okay, it takes a lot of computational power. But well, we do that. We use A3C as our deep learning algorithm to design to train this reinforcement learning algorithm, and because it is very hard to train. Actually, we use three-stage training of the reinforcement learning. At the first stage, it's like this. Okay, it's not possible to train this mobile robot from the scratch within the real environment. So we have to design an artificial environment for this robot to train. Okay, for example, those black dots are the moving obstacles. And bigger dot are the bigger obstacles. Small dot is small obstacles, and this purple dot is the mobile robot, and this yellow dot is the this blue dot is the goal. Okay, so we train this. We automatically generate thousands and thousands of this kind of environments, and train this neural network, and eventually when this mobile robot grow up like a kid, okay, when this mobile robot grow up, and we make the environment more and more complicated, and eventually this robot has the basic capability, then we send this robot to the real environment to train this robot. Okay, something like this. Okay. All right, so and we also have to design. Say, for example, if you are a doctor, well, in the hospital now we use this mobile robot to send the medicine from the pharmacy to the nurse station. Okay, so that the nurse station will open the door and dispatch the medicine to the patient in each room. Okay, so how do you call this robot? Maybe this robot is somewhere inside this building. So we design this QR code. So if you are going to, we could put this QR code at every space inside this building, so that the staff, if the staff want to call this robot, they can scan this QR code. Then the robot through Wi-Fi, this message will send to the robot, and this robot receive your QR code. Then this mobile robot know where you are, and then this mobile robot will travel. If it is necessary, it will also automatically operate the elevator to come to this place. and then because we designed this app for the robot, if you call this robot, then we will also at the same time we'll also give you another QR code. So you show the QR code to the robot, then robot know that you are the caller. So no one can ask this mobile robot to open the drawer except the caller and the receiver. Okay, so you show the robot to your QR code, and the drawer will open, and you can put your drawer into this. You can put the object to be delivered into the drawer. All right, and because your receiver also will receive the same QR code. So when the receiver show the QR code, the object placed at corresponding drawer will be open so that this receiver can only open the drawer which you put the object into, and the receiver cannot open the other drawers at the same time. Okay, so and we also design some voice control functions so that if it is necessary, this the user could use voice control to interact with the mobile robot. And we also have some gesture recognition functions so that we could also use gesture recognition function to control the robot with some simple actions. Okay. And okay, so the most difficult part is how to control the robot get into the elevator. So so when this robot use slam to move itself to the elevator, then the elevator, then the mobile robot first need to recognize the panel here outside of the elevator, so that it generally will push up, going up or going down, right? So we have to recognize this panel first, and then the mobile robot will use visual servo technique to go to the panel, then operates the elevator. Then the elevator will then when the elevator comes, the robot will detect whether the elevator door is open or still closed. If it is open, then the elevator will get into the elevator. Okay, and you know that the elevator usually is not that wide, so it's kind of delicate for the mobile robot to get into the going through the elevator door without bumping into the door. And then when this mobile robot gets into the elevator, it will also it will initiate visual servoing again to detect the panel, and then find and do some button recognition, find the floor, the button corresponding to the floor you want to go, and then press the button, and then when this elevator come to the floor you want to go, and then the mobile robot will wait until the elevator door open. This mobile robot use delicate algorithm again to go out of the elevator, and then switch the map from the original floor to the target floor, and then continue the journey. Okay, so this is the elevator operation, and from time to time we have to make sure that the motor control or the odometry is still okay. So we usually use this kind of route to make sure that the mobile robot doesn't need to fine tune. Okay. All right. So this is the visual servoing. Okay. So we use when this elevator, when this mobile robot detect this panel, then the camera will watch continuously this panel, and this mobile robot will move continuously to the panel. Okay, so this is called the visual servoing. And inside or outside of inside the elevator, we still have to do that. And this here we demonstrate that when we do visual servoing, it is possible that the pedestrian might block the vision, mobile robot's vision. So when the pedestrian move away, we have to remember where we were before it was blocked, and then we continue the visual survey. Okay, this is this experiment we did. Okay. All right. So then we design. By the way, we also designed this. We use 3D printer to make this robot arm by ourselves. So we designed this little 4 degree of freedom mobile arm to press the button for the mobile robot. Okay, something like this. And we also have a test environment inside our lab. Okay. All right. So this to precisely go to well, in the bigger space, we use SLAM to travel from one place to the other place. And then when the mobile robot move close to the target, then we use model predictive control to delicately control the motor so that the motor will move in a precise way to the target. Especially, we integrate the visual surveying with the model predictive control, and we kind of modify model predictive control so that this robot is able to. This is we call the bubble MPC. Okay, so we could this bubble can adjust the size so that we could follow the path designed by MPC. At the same time, we could still save some safe margin for the traveling, so that this mobile robot will not bump into the obstacles. Okay. Okay. So this is this is the way when this mobile robot is getting into the elevator. We have to use a very delicate mobile control algorithm using MPC, so that we could get into the elevator very smoothly. All right, so now let me show you some demo inside the hospital. Okay, so this person is calling the robot to deliver the object from the place she was located. So the robot hear the calling, then the robot will move from its parking space to the calling space. And as you can see, we could avoid, do obstacle avoidance. This is the wheelchair. And this person showed the QR code to the robot, and the corresponding drawer will be open. And then the drawer just use voice control to tell the robot that I'm done. So you can, well, actually this caller say thank you. Thank you means that, well, I'm done. So you can move now. Okay, so it will move to the target space. At the corner, the robot has to move slightly, because as you can see, it is very crowded inside the hospital. at a sharp corner, the mobile robot has to slow down, and now the robot will operate will operate the elevator. It recognizes the button and use visual surveying to approach the panel and press the button. And then it will back in and then come to the place right in front of the elevator. And then we'll get in the elevator. And then press the button again. As you can see, we also have some lighting and some signaling. And then when it is there, we will send a message to the receiver, and then receiver use his received QR code to show the robot, and the robot will open the door for him. Okay, so this is okay. Oops. All right. So the next thing, similar idea. We also work with a electric motorcycle company in Taiwan. Their idea is that can we use our robot to charge the electric motorcycle for this company? Okay, so this is the idea. This is the idea of charging motorcycle charging. Okay, so and this is all right. So this is another. We call it charging robot here. Okay, so without outlook. Okay, so without clothes, the charging robot look like this, and we still have 3D LiDAR here, and as you can see that we put this 3D LiDAR and also 2D LiDAR higher because we want to detect the parking space. There are so many cars, and so we don't. And those cars are not stationary obstacles. So if this car move away, then we notice that the environment changed a lot. So we have to install the 3D LiDAR higher so that the LiDAR will sense the environment instead of those cars or motorcycle park in the parking lot. Okay, we don't want that. We want the real environment. And as you can see, we have a charging we have a charger here. Okay, and the idea is that this mobile robot will carry batteries. Okay, so if any electric motorcycle needs to be charged, it will still call the robot so that this robot will carry the battery and then charge this motorcycle for it. Okay, so this is the idea, right? So why we want to do that? Because for example, in our university, we have about 2,000 motorcycles, and well, by the year of 2030, Taiwan will no longer allow gasoline motorcycle. Every motorcycle need to be electric. And so it is not possible for the school to build a power system with so much capacity so that in the morning when 2,000 electric motorcycle come to the campus, and then if they want to charge their robot, if they want to charge their motorcycle, our power system cannot afford it. So we have to. So the idea is that without modifying the power system too much inside the campus, can we build several charging robots so that if any motorcycle need to be charged, they can call it, and then this mobile robot will automatically go to the place and then charge the motorcycle for it. So this is the idea, and this is the company we will cooperate with want to do. Okay. So we put Aprotech. So we see this is the charging rope. This is the charging pole, and every charging pole we have a charging connector here, but there's no power connected to the connector, so that the campus power system can still afford it, because no electricity is used here. Okay, maybe see in the future we need to have 2,000 charging pole like this. Okay, and if we build the power system, connect the electricity to each of the charging pole, that's a big load. Okay, so our charging robot will come to the charging pole and then charge the motorcycle for it. And we don't want this charging robot to touch user's motorcycle. Okay, so as you can see, we have a charging connector, charging plug here. So if this is the motorcycle want to be charged, so the user will take this charging connector, plug into his motorcycle's battery. Okay, so and then this charging connector is connected with this connector here, so that when the mobile robot come to this charging pole, this charging plug will plug into this connector instead of the connector at user's motorcycle. So it will get this mobile robot will avoid contacting users motorcycle. So this is the basic idea, and so the SLAM, the SLAM, the obstacle avoidance are almost the same, okay, as hospital rover, except that we have to worry about how to control the mobile robot move to the charging pole, and this camera, the mobile servo camera, will recognize the charging connector and make sure that this charging plug will directly connect to the connector. Okay. So this is the basic idea, and we use we put a tag here so that mobile robots will, by looking at the tag, the mobile robot is able to tell the direction and the distance of this charging pole. Okay, and we still use visual throttle to control when we get into the neighborhood of this charging pole, then we use visual throttling to control, to delicately move to the connector. Okay. And so let me show you some demo here. Okay, so this robot is is parked at the corner of the parking space. When it is caught by the driver, then the mobile robot use SLAM to move to the place this charging pole is located. Okay. And as you can see, we put a LiDAR a little bit higher because we cannot sense this motorcycle, because this motorcycle might change the place from time to time. So we have to sense the environment instead, so that the SLAM will be more accurate. And then, and as you can see, we also use image recognition. And when this mobile robot see the tag here, then we use visual servoing to detect the distance and direction of the tag, so that we will know that where the connector is. And then we build a table to push the plug into the connector. And as you can see, it has to be very accurate. See, this is the charger. Okay, so when it is connected, then the charger starts. When the charging is finished, okay, then the mobile robot plug out the plug, and then go back to the place to wait for the next caller. And this is the SLAM. Okay, so this is charging robot. Okay, I have very limited time now, so finally I will talk about robot fish, because my time is not enough now. So I will. So basically, I use 3D printer to print the fish, and then I use two servo motor to mimic the swimming of a fish. Okay. So this is the first version of my fish. It's not that beautiful yet. Okay, and the way we do that is we put some camera on top of a pond, and then we record the fish swimming, and then we analyze the fish swimming, and we only have two. We decided to use only two servo motor. So when we analyze the video, fish swimming video, we select two joints in fish body, and we analyze the variation of those two joints while the fish is swimming, and then we mimic the fish swimming by delicately controlling the two servo motor. Okay, so this is the two joints we analyzed. Okay, and then we control the robot, the motor to mimic the swimming. Okay, so and finally this is the way. See, this is we have a pool in our lab. So finally we build this fish like this. Okay, and we also watch the diving and rising of the fish. And the way we control the diving is that we have another stepping motor inside the fish. When the stepping motor push the heavy object forward, then the fish the fish head will go down, and fish head go down. If we we control those two servo motor, then the tail the tail sweep. Then the fish can go down or go up. This is the way we control the fish, and so it's kind of complicated. So I have a video to show you how we build this fish. Okay, I like fish very much, so that's why I built this robot fish. And so we record fish swimming, and then we analyze the movement of the fish, and so we design our mimetic robot fish to mimic fish swimming, and we use 3D printer to print the fish, and of course all those tails and gills. And this is our 3D printing, okay? 3D printer to print those fish. And of course, we have to use waterproof. And we use SolidWorks to analyze the water flow on fish body, okay? And then they go back to the pond again and wash closely the fish again, and we analyze this. This is how we do it. Okay. All right. So this is something like this, and then, sorry. And interestingly, it's very interesting when we put our robot fish with the real fish. Even the real fish cannot tell whether it is true or not. Okay, and as you can see, all the fish gather around the robot fish, want to follow him or her. Okay, it's very interesting. And we also put some clothes on the fish. Our fish has a it's shown in the video, in a movie actually. So and we could also make this fish like doing fishing game without hurting real fish. Okay, we can enjoy the joy of fishing with our rod, and there's this is a magnet. Okay, and then we can enjoy the pushing of the fish. Fish struggling, something like this. It's very interesting. So you don't have to hurt the fish. You see, I'm doing fishing now in my lab. Right. And they can also we also use remote control to control the fish. We can allow 2 or 3 people to raise their fish. Okay, something like this. Okay, so now the fish is more beautiful. Let me show you the recent fish. As you can see, the fish now is more beautiful because now I learned some painting, and so we can paint, put some painting on the fish body, and of course we have more delicate 3D printer. Yes. Okay, so and interestingly, very interesting. Even the cat cannot recognize it is a real fish or not. We noticed that a cat is watching our fish. Okay. So, all right, conclusion. Well, we usually, in order to have AI, in order to have AI in the industry, well, we first need to have internet and IoT, and then collect enough data, big data, in every phase in every phase of the industry. And then when it is mature, then we will be able to, sorry. When we have enough big data, and then we know that it is about time to put AI into the industry. If we put AI into the industry and we find that production rates could be increased, life could be more convenient, and then we could commercialize the AI technology deeper and wider, and then we will have bigger market, more people enjoy AI, and the capital could be in place. And then if we have capital in place, then we have more capital to develop AI. So this is a positive cycle. So we notice that if we want AI to be ready for the industry, we have to notice those signs. And if those signs are very very clear, then we know that then we know that it is time to put AI into the industry. So so 3 stages for AI to be commercialized. One is that the first stage is the online market is well developed, and then sensing technology is well developed and also cheap. And then if individualized market is also well developed, then we know that it is about time for us to put AI. So this is my presentation. Thank you for your listening. I know that it's kind of rush, so I just roughly show you what did I do to integrate AI with machines. Actually, what I'm doing now is I am putting AI into our railroad. Okay, so because in Taiwan we are developing the so-called smart rail. So I have several projects integrating AI with rail industry. So this is even bigger, and it's even more interesting. So if I have some results, I will show you sometime, maybe next time. Okay. Thank you for your attention. Thank you.
Hello. Yeah, sir. I think so. As usual, your talk was very so wonderful and excellent. So some questions if the audience have, so they would like to ask from you.
Sure.
So can you come here? Actually, they can also, sir. Could you check your chat box?
Oh yeah. All right. Let's see.
Dr. Rakesh, if with your permission, may I ask a question to the professor?
Yes.
Yeah. My question to the professor, sir. Hello, sir.
Yeah.
Sir, do you have any research related to this AI, artificial intelligence, auto robo and all IoT in physical security, sir? Whether it's banks, whether it's ATMs.
I'm sorry, I don't follow you.
Dr. Rakesh, if you can convey it on phone, what I wanted to know is any
it's not. I
research
cannot hear you
from
very
their end
clearly.
for the for the security related, physical security related. Have they done any research where IoT plays vital role, whether
You mean
included in detection ATMs, banks, and all?
Rakesh?
Sir, could you type, sir, on the chat box? I think he can hear.
Yeah, okay.
So, sir is asking that do you have some real time projects which can directly related to some security and privacy, like
Physical security of ATMs,
Oh,
banks.
I see. I'm sorry, I don't have the project right now with related to security. I'm sorry, I don't have that.
Because using the IoT, we can do physical security. We can do away with the physical guards and replace that with the technology.
Yeah, I agree with you.
Yeah. So I just wanted to know, because I did some research and I had a real-time experience on this. So I thought if you have any, I wanted to know the latest trends from your sides.
Okay, this is not my specialty, so I don't know too much about security. Yeah.
Understood, sir. Yeah. Thank you, Professor.
Thank you. I'm sorry. Yeah.
Yeah. So some questions on the chat box, sir.
All right. Let me see.
Sir, thank you for the wonderful session, sir. Sir, I was inquiring about the hospital robot. So what if there are more people in the elevator and they need to exit on a different floor? Will the robot be able to step on the correct floor?
Very good question. So we found that if the elevator has one or two people, then the robot can get into the elevator. But we noticed that if there are more than two people, we tried not allow robot get into the elevator, because we are afraid that when this robot press the button and then change the direction toward the door, we might hurt people inside the elevator. So far, the way we control the robot is that we use LiDAR to check the number of people inside the elevator. If there are more than two people, then the robot will skip this elevator.
Okay, sir. Thank you.
Thank you.
Anyone else? Okay, sir. So thank you very much, sir, for your wonderful sessions.
Thank you.
So I hope the practical